Hey John. Hey everybody, it's John. So I said I was going to start this video by going through how to solve for t here. So we want to know how long, how many minutes they should wait before we deliver the coffee to a customer at McDonald's. And in the last video we solved for k. And in this one we want to solve for this t value. We know that our desired temperature is 125 degrees. So I'm going to start by subtracting 72. So 125 minus 72 is going to give me 53. So I have 53 equals 108 e to the negative 0.150t. Now I need to divide both sides by 108 to get the e term totally by itself. So we have 53 divided by 108 equals e to the negative 0.150t. I'm just going to double check. I don't think it reduces, but I'm just going to double check to see if I can rewrite 53 over 108 to a more reduced fraction, which I do that by plugging 53 divided by 108 in the calculator. It gives me a decimal, and then I hit answer. I hit math frac, which gives me answer converted to a fraction. And it's giving me the same 53 divided by 108, which means this is the most reduced form of this particular fraction. So now I need to get at this exponent here. I've gotten e to the something reduced as far as I can. So I'm going to go ahead and ln both sides, or I'm going to use my definition of a logarithm to rewrite this. In either case, I end up with negative 0.150t equals ln, which is log base e, of 53 over 108. And so now I almost have t by itself. Remember that ln of 53 over 108 is just a number. It's the number that I would raise e to get 53 over 108. And so your calculator will give you a decimal. Just don't turn it into a decimal yet, because you want your final answer to be as accurate as possible. So if we leave it in this form, we're going to get the most accurate possible answer at the end. So my last step is just to divide by negative 0.150. So if I was going to put this into Pearson, I might just put it in as negative 1 over, well, I might just put it in as ln of 53 over 108 over 0.150. Typically, we don't like to have decimals within fractions. So at this point, I would probably just change it to a decimal. So we have negative ln of 53 divided by 108 divided by 0.150. And that gives me 4.746. So you want to wait that many minutes before you give customers their coffee from the pot. Otherwise, they might burn themselves. Okay. So let's move on to some properties of logarithms. Now these properties come directly from the exponent rules. When I multiply like bases, I add the exponents. But what does a logarithm represent? It represents the exponents. So when I'm adding two logarithms together that have the same base, I can just multiply what's inside the logarithms together. Likewise, if I'm dividing inside a logarithm, I can subtract two logarithms of the same base. And then we have another exponent rule, which is if you raise a power to a power, you multiply the exponents. So I'm raising what's inside the logarithm to a power. That's the same thing as multiplying the entire logarithm by that power. So these are three properties of logarithms that we're going to use to do some stuff. You're going to use them a lot more in calculus. So the applications that we do here are going to be a little thin, probably not going to feel like they're applicable, but let's do it anyway. So here we have log of 2 is equal to 0.301 and log of 3 is equal to 0.477. Now again, these are common logs. This is log base 10. It's not written, so we're assuming that's true. And assuming that this is true information, we're going to use the properties of logarithms to find out the values of these without needing a calculator. So the first one, log of 2/3, I can use this second property here to rewrite log of 2/3 as log of 2 minus log of 3. Now we know log of 2 is 0.301 and log of 3 is 0.477. And I mean, I'm going to use my calculator anyway, but I'm just not going to use the logarithmic function in my calculator. And that gives me negative 0.176. So log of 2/3 is approximately equal to this. And I did that without just using the properties of logs. And before we had these calculators, you would have to look up the value of a logarithm in a very large book. And so this would definitely be a faster way to find the value of a logarithm if you knew a couple of values of log. Okay. We can do log of 9 two different ways, and I want to show you both. First, we can think of log of 9 as log of 3 times 3. And so we can use the first property of logs, which says if I'm multiplying inside, I can add outside the logs. And log of 3 is 0.477, and log of 3 is 0.477, and 0.477 plus 0.477 is 0.954. So log of 9 is approximately equal to 0.954. So the second way we can do this is we can think of log of 9 as log of 3 squared. And we can use the third property of logarithms that says that I can take this exponent and bring it down in front. So 2 times log of 3 should give me the same answer if math is not contradicting itself, which it never does. And adding 0.477 to itself is the same thing as multiplying 0.477 by 2. And so you can see how this property works. It does work. So both of these properties yield the same answer. So log of 6 can be thought of as log of 3 times 2, which can be log of 3 plus log of 2. And so 0.477 plus 0.301 gives me 0.778. All right. So what we did there for each of these is we sort of expanded the logs. We expanded that log, we expanded this log, we expanded this log right here. So this idea of expanding becomes very important in calculus. When you have a complicated derivative that you want to take, you can expand. And so that's what we're going to do here. So this has the 10 written. We don't have to have the 10 written there. We can just write it log of 7x cubed. If I want to expand this, I want to make it as many logarithms as I can. So the first thing I'm going to do is notice that 7 is being multiplied by x cubed, and that first property says if I'm multiplying inside, I can add outside. But then I also want to expand in the sense that if I have any exponents inside the function, like I do here, this 3, I want to expand it by bringing it out in front. So my final answer here would be log of 7 plus 3 log of x. Now notice how I split it up first and did this step first, because this 3 is not talking to the 7, It's only talking to the x. It's the x that's being raised to the exponent. It's not the 7. So I have to split that up first, and then this 3 goes in front of only the log that has the x in it, because that was the only thing that was being raised to the third power. So this would be expanded. Condensing is just going the opposite way. As long as the logs have the same base, I can go ahead and use the properties in reverse. So log base 5 of 6 minus log base 5 of 4, since I'm subtracting outside, I can divide inside, which I would want to reduce this to its lowest terms. That would be condensed. Now, when you're done condensing some logarithms, you should only be left with a single log. So if you have log written more than once when you're condensing, that probably means that you did it incorrectly. And so that's a good check for your work when condensing. So let's do some more difficult expanding and condensing. I'm just going to go through and do the answers. Again, you can quickly, you can pause, you can go back, you can watch this as many times as you want to figure it out. But basically, since I'm multiplying the 3, the x, and the y squared, I'm going to have 3 different logs. I'm going to have log of 3 plus log of x, then plus 2 log of y, and this 2 came from the exponent coming down in front of the y. Okay, same thing here. Log of 7 plus 3 log of x, that's the exponent there, that was only talking to the x, plus log of y, plus log of z. So when you're expanded, you want as many logs as you can have. There's 4 things being multiplied in here, so I should have 4 separate logs. Condensing, I only want 1 log. This would be log of x over 3. This one would be log of 2 over x squared. So this comes up first to become x squared, and then we do the division with the minus. Okay. And even more. So expanding is what we're going to focus on in this course because that's what you're going to need for calculus. But condensing is going to be needed when we solve logarithmic equations in the next section. So I'm just going to expand these real quick. These have natural logs, so ln of 10 minus ln of 9 is the first one. Let's number these. So number 1. Number 2 is going to be ln of 6 plus ln of x minus ln of 5. Anything in the numerator is being added, is positive. Anything in the denominator is negative. Number 3, there's actually an exponent here. Instead of writing the square root, I can think of this as a 1/2 power. So this would be 1/2 ln of 3x plus 2. I'm adding inside the logarithm. There is no property for that. So this is my final answer. If it was the square root of 3x times 2, then I could expand what's inside here a little bit more, but I'm adding inside the log. There is no property for that. And finally, this one's a bit of a doozy. I'm going to bring this exponent is going to go with this term. This is a cube root, so I'm going to think of this as to the 1/3 power. And so we have ln, we have 2 ln of x squared plus 3 minus ln of x minus 1/3 ln of x squared plus 1. Now, if you had wanted to, you could have done 2 ln of x squared plus 3 minus, in parentheses, ln of x plus 1/3 ln of x squared plus 1. This would be valid as well, but we always want to try to get rid of as many parentheses as we can, which makes this answer a little bit better. Okay? So that's all I have for you on logarithms, and I will see you in the next series of videos on solving logarithmic and exponential equations.